Hello.
There you go.
It's my distinct pleasure to welcome our speaker today, Dr. Grant Brown from the University of Iowa in the Biostatistics Department. So Grant is here. He's an academic brother of a former colleague of ours, Aaron Porter, and he's working with Katie Martinez and myself on some SER type models, statistical inference. In particular today, he's been kind enough to join us to talk a little bit more about his own specific work on ABC approximating computation for these types of models. And I'll just let him go and stop that.
All right. Well, thanks, Steve. Thanks so much for inviting me. It's been great to meet everyone. An interesting talk. I don't know that I've ever talked about stochastic compartmental models to an audience with quite so many applied mathematicians. So I hope that this being a Bayesian talk, an approximate Bayesian talk, that won't annoy the frequentists, and then being a statistical talk won't annoy the applied mathematicians too much. But this is work, I've called it Working with Approximate Bayesian Computation and Stochastic Compartmental Models. It's sort of a collection of a variety of different things that I've been working on for a couple of years now. Joint work with, as Steve mentioned, Aaron Porter, my mentor Jacob Olson, as well as several students, Jessica Hinman, who was a master's student in epidemiology, who helped get the paper associated with the primary contribution of this work out, and Natalie Langenfeld, my current graduate student, who will be graduating very soon. So these techniques are really the result of efforts to solve a particular problem. I didn't come to them with a particular theoretical interest in the structural form of the model, but rather an interest in actually fitting a model to data. And if you've seen epidemic data, you'll know that there are a lot of challenging features of those kinds of data sets. So specifically, I started this work looking at influenza, then moved into Ebola as that outbreak developed in West Africa, and I've since analyzed data sets including chikungunya and cholera, and we have ongoing work with leishmaniasis in northern Brazil. Stochastic compartmental models, as I think many of you know, it sounds like there have been a couple of talks, at least somewhat related to these topics, are statistical models rather than deterministic ones. And they're compartmental because they allow us to break up disease processes into disease states. For me, the reason I'm particularly interested in statistical inference, well, I guess the reason is that I'm trained as a statistician, right? But the reason I like doing statistical inference is because of that inference piece, right? I want to analyze a data set and be able to actually make inferential claims about biologically meaningful parameters. So that means doing things like quantifying whether or not a disease is expanding or contracting in a particular context, in this particular spatial location. It means evaluating public health interventions. It means uncovering important biological associations with phenomena like weather, for example. Now, stochastic techniques are great for that reason, although, as many of you know, they do come with a large computational cost that can be sometimes overwhelming. So, with that in mind, everyone who does Bayesian inference of one sort or another tends to have a particular kind of favorite computational speed-up technique. Some people are very into approximate Bayesian computation, which is something I focused on. Some folks think about variational Bayes as an option. Some folks make simplifying assumptions about independence in a model and sparsity. Other folks are using INLA. There are a million and one sort of different techniques that people use in different contexts to try to get some speed up. So hopefully this talk will point out maybe an interesting technique that you hadn't considered, or if you have seen ABC before, maybe some additional generalizations to the way that we use approximate Bayesian computation in practice, as well as pointing out some of the things that currently give me headaches. There are a number of important drawbacks with just about every approximation that we make, about every computational technique that we use. And so it's important to be aware of that up front and maybe start thinking about potential strategies for solving those problems. Okay, so some brief background. Apologies if this is a review for some of you. But epidemic models come in many shapes and sizes, and we often come up with a sort of alphabet soup acronym to describe them. You've heard of SIR, SEIR, SEIRS, and any one of a number of other capital alphabet letters, generally describing disease states. We break a disease process up into discrete compartments or biologically meaningful states that the disease can be in, and then we come up with a catchy acronym for it, and that becomes the name of our model. These, of course, have their roots a very long time ago in deterministic systems of differential equations. So a common class that I have been focused on is the SEIR and correspondingly the SEIRS model class, where individuals move from susceptible, where they are capable of contracting a particular disease, to exposed, which counterintuitively means they have contracted the pathogen of interest but are not yet spreading it. That allows you to model diseases that have a latent period. Infectious, meaning they're capable of transmitting the pathogen removed. And then for some diseases which do not either result in mortality or confer permanent immunity, individuals can move back into the susceptible state. These are far from the only choices. Now, spatial SEIR models add an additional dimension. So instead of thinking about this as just a temporal process whereby members of our population move through discrete states, we instead have that model over space. We essentially add an additional index. Over time, we have a series of difference equations. And those of you who have worked with difference equations such as this will notice that this particular model makes an assumption that is always wrong, but usually not a big deal, and that is that the population that we're studying is not changing in size over time. And for most epidemic type models, that's usually fine. The population is large, the number of people who are being removed from the population is not enormous by a death process, for example, or by a migratory process. And so that simplifying assumption just allows us to move on and fit the model and get some reasonable results. Okay, so in the stochastic setting, we model those as binomial random variables, and you can tell by the superscript what transition we're talking about. So a binomial will have a size, so the new individuals, S star, that move into the susceptible compartment, are drawn from the previous removed individuals according to some probability. You can identify which probability is which by the superscript. This is going from R to S. And you can tell what kind of a temporal or a spatial index is involved by taking a look at the subscripts. So here we have pi ij, meaning that probability is allowed to vary over space and time. The real core of a lot of these models, where we spend the most of our time sort of pinning down what might be driving the transmission process, is really here. Because this is the probability of exposure. It varies over space and time. It's really the fundamental core of that epidemic that we want to influence if we're thinking about public health problems. And it's often one of the most difficult things to estimate as well. We could also allow the latent period associated probability or the recovery probability to vary over space and time, but often that's really just motivated by the pathogen of interest, and so we generally use external information to motivate those things. So in addition to that process model, we introduce a data model. And this is a notation that is often used in hierarchical modeling techniques and statistics. And I think it's useful because it's very easy for us to slip into the assumption that the data that we observe is actually reflective of the underlying phenomenon. It's almost never actually the case. So in the simplest setting, our observed data, which we denote for simplicity Y, could be a direct and error-free observation of the underlying count. So for example, we might observe newly infectious individuals, I star, people moving into the infectious state. That's often in biological problems associated with an onset of symptoms, for example. That might be recorded in a surveillance data set in that way. In reality, though, there's probably some sort of underreporting. So we could think about Y as being modeled as a binomial draw from the total number of individuals entering the infectious state at that particular time. It could be modeled simply with error, in which case we might introduce some sort of a discrete over-dispersion, but nevertheless a data model component is an important part of these models. Now the interesting piece, the spatial process. The spatial process in spatial SEIR models, as I've sort of formulated them here, is introduced into this exposure probability. And for those of you who were at the Math Bio seminar earlier, this really is different than the kind of models that we're working on with Steve and Katie, which explicitly model movement. Here what we're thinking about is a sort of epidemic intensity structure, and then a spatial structure over that epidemic intensity. So I won't go into too much detail, but the form here depends on a component that models intensity within a particular spatial unit. We're modeling disease over discrete sort of administrative regions, as well as a component drawn from the same functional form from other spatial locations with which individuals can come into contact. And that is governed by two things. First, what I've been calling very informally distance matrices, which in the simplest case could be a matrix of indicators that tell you whether or not a pair of discrete spatial locations share a border, for example, or could be something more complicated. We'll see examples of that, as well as a single autocorrelation term. So here we have a very sparse parameterization of what that spatial process looks like, which allows us to actually fit the model. If we had too many parameters, things get very difficult very quickly. We're trying to solve problems like that. This talk isn't there yet. So this eta ij, the sort of intensity term, we actually formulated as a matrix, and that's what allows us to use these distance matrices as a sort of smoothing operator over those things. And it incorporates a couple of different terms. It incorporates the infectiousness of a pathogen, it incorporates the contact distribution, and it incorporates the infectious fraction, right? Because if you think about what has to happen for an individual to become infected in one of these models, you A, have to contact an infectious person, so the probability of that event depends on how many infectious people there are in a particular context. You have to end up actually contracting the infection as well. And the probability of becoming infected at all is the sort of combination of that kind of an event over some total number of possible contacts. Here, sort of making the simplifying assumption that we can model these sort of homogeneous contacts at least within some sort of a discrete spatial unit. Okay, so another important component of the spatial SEIR model specification process is the transition. And this is one of the aspects that Aaron really made a lot of contributions to in his time working on this. So transition from the exposed state to the infectious state, which governs the latent period, and infectious state to the removed state can be modeled in a lot of different ways. And the simplest way is something I often still do. It's often good enough, even though, again, it's almost by definition biologically untrue, and that is just to assign a constant probability of transition for all individuals in those states at a particular time. And if you think about that, it's sort of unreasonable because it means that no matter how long an individual has stayed in a particular disease state, their probability of transitioning is exactly the same. So it induces on this discrete scale a geometric distribution on the compartment membership times, which is sort of completely unrealistic for biological problems. If you read clinical literature about diseases, they'll often state that individuals remain in the disease state for A to B days. It's often sort of an interval time, or an average of blank with an error of some other number. So it's unreasonable. You're never going to describe a transition distribution that actually makes sense with that assumption, but it has very few parameters. It has very few parameters, which is an attractive feature if you actually want the models to converge. And it often tends to not matter too much. So another approach is to assume a more interesting, potentially nuanced distribution for the latent and infectious period. And this is something that I have done in cases where that latent period needing to be at least a certain amount matters for the disease dynamics. It's worth doing. If that doesn't matter for your transition process, it's probably worth waving your hands a bit. And this is one of Aaron's big contributions, his path-specific approach. It essentially introduces an additional dimension that allows you to model the transition process from one state to another based on how long individuals have been in a particular disease state. So it is biologically reasonable. It's actually quite easy to simulate from, but it does introduce more parameters. So instead of essentially making a binomial draw at each time point from the current population in a particular disease state according to some hopefully biologically reasonable probability, instead you break it up into an additional dimension tracking the counts of people who have been in a compartment for a certain amount of time. So it's not an individual level model, but it does break up each of those disease states into an additional dimension. And you can use this formulation to construct an overall, at whatever your discrete time interval is, count of newly infectious individuals as a combination of those who transitioned. And if we have, let's say, a weekly model, those who transitioned on day 1, day 2, day 3, day 4, day 5, 6, and 7. So that's path-specific transitions. There are a couple of common choices for that distribution, although recently when I've been using this, I often simply use a uniform because that's the scale at which biologically meaningful information is given. The WHO says that Ebola becomes symptomatic between, and I'm going to make these numbers up, I know this is being recorded, so don't quote me on this, let's say 5 and 12 days. You can incorporate that explicitly into this formulation. Okay, so these varied processes highlight one of the things that I really like about working with this particular class of techniques, right? So I didn't write down a comprehensive model. By using Bayesian hierarchical modeling, I'm able to specify what I think is probably a reasonable conditional specification. So I break it up into the individual components of the process, specify how they behave conditionally, and then combine them using Bayes' rule. So each process is structured based on literature or WHO website or consultation with experts, and prior distributions can be used to inform model parameters. Now, I've put must in parentheses over here, because in practice, those of you who've worked with these models know that even if you are doing your best to quantify your potentially vast uncertainty about a complicated problem and you include vague prior distributions, the model's not going to perform very well. We really often do need to include highly informative prior distributions about some of these epidemic parameters. So in the simplest setting, where I'm thinking about those exponential or geometric transitions for the latent and infectious periods, I have had very poor luck trying to estimate those from data. One would need a very large data set to try to pin those down effectively. and that's something that we simply don't have in a lot of practical epidemic disease modeling settings. So instead, we do our best to try to quantify based on what's known in a scientific sense about a pathogen and the disease process, and include those at this stage. So I really can't emphasize that enough. We are including informative priors, and it's on purpose. Working with the actual analytical form of these models is really quite straightforward. We have a nice Markov structure in time, so if I'm trying to specify the joint distribution of all my compartment parameters, it's easily accessible as the product of an initial state and then all of those conditional distributions that we specified in the difference matrices and their corresponding binomial components. So at first glance, this looks pretty straightforward to approach. We can write down a model, we think it's reasonable, it's relatively high level, and we should be able to use standard computing techniques. So it has a couple of advantages. It's biologically motivated, it's adaptable to many disease processes, it's easy to incorporate spatiotemporal covariates, and I'll show you examples of that as we move through the talk, and it's easy to incorporate many spatial association structures. That's why, the D matrices here have an index, and you can even add an additional index for time in those context structures. So it's quite easy to extend, easy to understand, easy to write down, and even easy to write out the full code for an MCMC sampler over all of these unknown parameters. There are some serious drawbacks, and this is sort of the point of the talk. The spatial structure is pretty sparsely parameterized. So if you think back to the talk that we had earlier in the math bio section, you really have to have a good idea of what those D matrices look like. You have a single parameter for each, so you are allowing yourself to estimate the relative contribution to various components of that probability, but the degree to which that has flexibility depends on how many of those D matrices you include, whether you allow it to vary over time, and then, if you've done so, you have to be fairly confident that that's a reasonable functional form for that probability, which in practice is quite difficult. So that's something to consider. Additionally, it can be very cumbersome to explore different compartment structures. So what I mean there is if we add different letters. So if a single latent state, for example, is not a reasonable description of an epidemic phenomena, and we needed to account for the fact that some individuals transition immediately, some individuals then maybe move directly to the recovered state, let's say. If, for example, it's possible to acquire a pathogen and then develop immunity without ever becoming infectious. So that's a biologically plausible phenomenon. If you wanted to take code that was written to fit a spatial SCIR model and then go and fit a different model, there's a lot of bookkeeping to do. So that's sort of a caveat for the software package I would have mentioned. It only does spatial SEER stuff, so if you're not doing that, it's not going to be useful to you. Many apologies. And the last one is probably the most important, because the rest of this is bookkeeping. There are lots of parameters. And by lots of parameters, what do I mean? I didn't specify many covariates. I didn't specify all that many spatial autocorrelation terms. So where does the latent space come from? What is the parameterization problem that we have? So if we assume that we have J spatial locations here, so that's often counties, states, nations, etc. We have T time points, and we have a non-degenerate data model. So we're not just assuming that we directly observe one of those compartmental phenomena. Then we have T times J observations. That's our Y. It's the number of spatiotemporal points at which we are observing something that tells us something about this epidemic. We have 4 times that, latent compartments, SEI and R. That gets worse if you add more compartments. We have some number of spatial autocorrelation terms, some number of exposure process covariates, some number of reinfection process covariates, and 2 to 4 transition process parameters, depending on whether or not we are modeling this as an exponential or using path-specific machinery. If we add path-specific, we can add quite a few additional parameters. And in addition to these things that we're giving distributions, these models are highly structured. So there are a whole lot of things that you have to derive, right? If I give you the starting points of all of the epidemic parameters, all of the epidemic compartment counts rather, and I give you those update equations, S star, E star, I star, and R star, you're then computing SEI and R. And so that's an additional factor of computation that scales with space and time. Now, there's an additional wrinkle to this, right? Because this many parameters doesn't actually seem that bad for many types of models, but there's the additional problem that they're discrete. A huge component of these are discrete parameters, which makes many of the strategies that we would usually use to deal with a high dimension unavailable to us, or at least unavailable to us without some additional approximation that becomes unreasonable for small counts. Okay, so again, it's not difficult to write down the form of the kernel of the posterior distribution, very easy to do. Factor out full conditionals and implement a kind of naive MCMC algorithm. That's very straightforward to do, and that's in fact where I started working with these models. I spent a lot of time writing down as fast of an MCMC algorithm as I could, and really couldn't fit problems with greater than 5 or 10 spatial locations. And even then I'd be waiting for quite a long time, after quite a bit of work trying to make reasonable, intelligent proposal distributions for that MCMC sample. They just perform very poorly as your dimension increases. And this becomes particularly severe when you have lots of spatial locations. Okay, so that brings me to ABC. I'm led to understand that many of you have seen ABC before, but I am going to run through the basics. So approximate Bayesian computation is an interesting sort of set of techniques, and when I first encountered it, I thought it was sort of a general catch-all term, because of course there are lots of different approximations that we use in Bayesian inference. Instead, this is actually capital A, capital B, capital C approximate Bayesian computation, an idea introduced by Rubin in the interestingly titled Bayesianly Justifiable and Relevant Frequency Calculations for the Applied Statistician. So it's quite a title. For those of you looking to orient yourself in ABC literature as it stands now, I would recommend a good review paper that came out by Mark Beaumont in 2010. And as we've been discussing, there are some really interesting theoretical results introduced by Pierre Delmoral as well. I'll reference some of his work as well. So the original algorithm is no longer of much practical use, but it does give some of the important intuition as to how the technique works. So again, we're in a Bayesian setting, so we have some parameters. I'm going to call those capital theta. So this is the vector of parameters that I have. I have some data, and here in my compartmental setting, of course, the data is going to contain a whole bunch of other latent stuff as well. But I have some way to generate new replicate data sets conditional on a value of those parameters theta. And then the goal of Bayesian inference is to estimate the distribution, the posterior distribution of those parameters theta conditional on the observed data x. And so the rejection algorithm proceeds as follows. We draw theta from its prior distribution, that's pi. We then, conditional on that value theta, draw a replicate data set x. So x and theta are then drawn from their joint distribution. And then if x is exactly equal to our observed data y, here you should have red flags going off in your brain at about that point, store the value of theta, and then repeat those steps until you have enough stored values of theta to consider them a reasonable sample from your posterior distribution. So this third step here is sort of the algorithmic equivalent of conditioning on your data. That's what we're doing. We're generating a joint sample and then conditioning on the observed data y, and out comes a nice and tidy sample from our posterior distribution theta. Now, that's conceptually very clear and not very practical in most circumstances. So for continuous data y, except in sort of degenerate settings, the acceptance probability is going to be 0, so that's not going to be useful to us. So a more practical algorithm is given by introducing a set of summary statistics. And there has been quite a lot written about these summary statistics, and I'll address some of the ongoing difficulties towards the end of the talk. So instead of conditioning on exactly observing some new data y that exactly match, or instead of conditioning on our simulated data x being exactly equal to our observed data y, we instead condition on some distance metric between a set of summary statistics on our simulated data, summary statistics on our observed data being less than some particular epsilon, strictly greater than 0. And by doing so, we then declare, well, then that's approximately a sample from our posterior distribution. So this is the approximate algorithm, this is the comparison step, and this does produce approximate samples from the posterior distribution with, as you can guess, many caveats. Right? There are caveats concerning the magnitude of epsilon, caveats concerning the choice of the summary statistics and the kind of distance metric we're using here. The answers to those problems is going to depend on your problem. But I do know that several people in this department have actually used a variant of this algorithm to some effect. So if your algorithm, or if your problem is not so large or difficult to simulate that this rejection algorithm works, then it's simple to do, easy to check, hard to screw up. So useful tool if it applies to your problem. But I think it's also important to think about when this is going to have potential issues. I also want to highlight some additional notes. So these algorithms themselves highlight why ABC is sometimes called likelihood-free inference. So we're never actually evaluating the kernel of our posterior distribution, right? We're generating replicate data sets from this F, the data generating mechanism, likelihood. but we're never evaluating that thing, which is kind of nice. And that means that this algorithm can be used in settings where we don't have access to that, either computationally or just practically. Nevertheless, I mean, it is applicable even when we do have access to those.
But to generate that, you need some information about likelihood. It's still expensive, right?
That's a good question. There are pathological cases where you can generate data and not analytically characterize the likelihood, but I do not remember the specifics. I can look up the reference and send it to you. I haven't encountered it, so I haven't concerned myself with it. But there actually are such cases that you cannot evaluate. It's not just an issue of computational expense. In point processes is where this arises. Now, in cases where the kernel of the posterior is impossible or costly, this might be attractive even if we can evaluate it, and that's what we discussed earlier. The other thing that's really nice about this algorithm in the era of modern parallel computers is that these simulations are entirely independent. They don't require any interdependence among those samples' data. It's embarrassingly parallel. You could start up 10,000 computers, each one, as long as it knows what the prior is and it knows what the data generating mechanism is, then it's able to generate these samples and accept or reject them, which is great. Even so, as you might have guessed by all my hinting, yeah?
So what happens when the dimensionality of the parameter space is really high? Is that...
Then you're going to have a bad time. Exactly. So even so, there are sometimes very severe efficiency problems. And the scaling of the dimension of the parameter space is definitely a problem. The other problem is the density of this region that you're generating here compared to the density of the region where you'll generate epidemics or replicate data sets conditional on epsilon being less than that window.
And also you cannot use this with improper priors, right?
Yeah, exactly. But why would you use an improper price?
Well, I know people who do.
So, as we were mentioning, if the prior distribution is diffuse relative to posterior, which I would hope it is, because we hope to learn something from our data, the proposals from high theta will only infrequently occur in those regions of high density, and you can imagine that that's a phenomenon that's going to scale very poorly with dimension. So there is quite a bit of literature exploring the way in which the performance of these algorithms degrades with dimension. Some of that's given here. Fortunately, they also propose solutions, and that's going to bring us to our next topic. So sequential Monte Carlo, there are a lot of terms surrounding sequential Monte Carlo. It's used differently in different fields, but it's one of the most common approaches to improving efficiency. If you read that Beaumont paper, other folks have used MCMC techniques, which I have found totally ineffectual, but maybe it's just my lack of programming ability. There are regression techniques, density estimation techniques. I've had a lot of luck with SMC, also sometimes called in different contexts particle filtering. The general idea is to try to improve on that sampling process, improve on the process by which we propose parameters from which to simulate replicate data sets. So we base new theta values on the currently accepted samples. We start off in the same place, generating parameters from our prior distribution. Some of those are going to generate replicate data sets, which improve on, which generate replicate data sets that are relatively close or closer than the first simulations we take. And then once we have a set of parameters that did okay, they improved on our general simulated replicate data sets, then we resample from them according to a scheme that allows us to preserve the target distribution of interest. So as the algorithm progresses, generally speaking, this is not always true, the required tolerance decreases. So the epsilon comparison window is going to decrease. So it has sort of an analogy to simulated annealing, right? You start off at a very high temperature, and then you cool it down and require closer and closer simulations as your parameter set becomes enriched in regions that are generating data sets close to your observed data. So there's a long history here. This appears, based on my ability to read the literature, to have been introduced by Pierre Delmoral in 2006. Initial adaptation to ABC was pursued by Sassone in 2007, and then in 2009 it turned out that there was a bias in that original paper. I've still seen some people using it, so don't use that original algorithm unmodified. But in 2009 that was corrected, and then they've been revised since. Pierre Delmoral introduced an adaptive approach to selecting those epsilons, because you can imagine having to figure out what temperature to choose is kind of a pain sometimes. So that's they've introduced a nice algorithm there. And then epidemic models were first pursued in 2015, and a number of folks right around the same time, including myself, pursued applying these to spatial epidemic models. So the paper that we put out came out just recently, 2018. So the ABC SMC algorithm, it looks a little bit uglier, but it's actually not too bad. it can be summarized for a scalar case in a pretty simple way. So you start off basically in the initial rejection case. We simulate new replicate or new particles. Screwing up my terminology here. We simulate parameters from our prior distribution and use each of them to generate a replicate data set as before. And we do that until we have a sufficient number of those particles that meet our first epsilon criterion. So this is generally not very stringent. We pick a very large epsilon. In fact, what I generally do is just simulate a batch of particles and set epsilon to be equal to the maximum value among that current set. It's a good starting place. Then we have a weighting scheme. So the weighting scheme is derived, but this first step we give them equal weight since it's drawn from the prior. We're going to modify that using importance sampling in subsequent steps. So as the algorithm proceeds, so as I increases, our iterations increase, we have a new epsilon target. We draw our proposed parameters from the set of previously accepted parameters according to the weights that we specified. And then we draw a replicate data set, then we perturb those according to some kernel. In most cases, this is just a Gaussian kernel. And we draw replicate data sets from those newly perturbed parameter values. So by doing that, we have potentially a much better set of simulated data sets. But the ABC argument relies on having simulated the parameters used to generate them from the prior distribution. And so the way that that's corrected is with an importance sampling argument. And that's where these weights come from down here. We calculate weights designed, and there are actually a number of different weight specifications that you can use and different variants of this algorithm. But they're, generally speaking, derived from an importance sampling argument to account for the fact that we're not generating them from the prior distribution. Then we increment the iteration counter and just repeat that until some time. That's the general sketch of the ABC SMC algorithm. Fairly easy to code up in most problems. So, a couple of things to consider. We did just take one of those attractive features of the rejection algorithm and throw it out the window, right? We created a sequential algorithm. But nevertheless, we can still get a lot of benefit from parallelizing components of this. So the computation time is strongly dominated for anything you would bother using these techniques for by the simulation step. So you can parallelize the simulation of those replicate data sets X within each sequential iteration. The way that I've tended to do that is via a batching process, because it minimizes some of the communication overhead that you have to worry about when parallelizing things. So you sample some much larger number than the number of target particles. B, you distribute the work of simulating data for them over some sort of parallel infrastructure, whether that's threads or processes or jobs or what have you. And then if sufficient particles were accepted, collect the results, reweight them, and go back to the top. So the middle part that's computation intensive is parallelizable. We still have this sort of sequential sandwiching of that component. Yeah.
So what's the advantage of taking the difference between the sum and expectations? Why not, for example, the difference of the vectors? That's what we want.
We're going to get to that. We're going to actually have a very good example of why that's a potentially problematic thing to do. After I first introduce a software package that I wrote that does exactly that. So often that's a good place to start. There can be some problems with it. Did you read my slides ahead of time? So there are, of course, a million variants of this, and there's also different terminology that's used depending on which literature you're reading. But this is a fairly representative algorithm from this algorithm class. Let's see how much time we've got. I'm going to skip some of this in the interest of time. I'll just say one thing, is that the Delmerol paper attempts to set an adaptive epsilon schedule. So if you find setting an epsilon schedule problematic, that might be one thing to consider. Okay, so terminating conditions. Ideally, we want to pick some actual epsilon that we care about. That's going to vary in scale depending on the problem that you have. But it's also going to be impractical. I know because I have never once actually reached a terminated epsilon that I was happy with. The constraining factor was how small I could make it before I lost patience. So in practice, this is not your terminating condition. Your terminating condition is something like a maximum number of algorithm iterations, a maximum number of batches resulting in insufficient particle updates, and you can vary batch sizes and number of particles. But those terminating conditions are fairly practical, and they give you an interpretation in terms of the acceptance rate, right? So you're basically running this to a terminating acceptance rate in one way or another, and that's, in my experience, been fairly practical, absent the ability to run my computer for non-finite amounts of time. So why would I be talking about ABC SMC at all in this case? Because we're talking about compartmental models that have a likelihood. The problem is that large discrete latent space that I mentioned before. So of all those parameters that we talked about when we were counting parameters, how many of them are actually needed in that theta to generate replicate epidemics? And the answer is very few. So in the problems I've been concerned with, the sort of basis set of parameters needed to simulate epidemics is very small. So it turns my large, ugly, discrete problem into a small, continuous problem, which is very nice. A very nice way to reduce the dimension. And none of those parameters also necessarily scale with the number of time points. I mean, that's a bit disingenuous. Larger spatial contexts and longer epidemics probably require more complicated intensity structures to describe adequately, but there's nothing that necessarily scales with space or time in either of those. So if we generalize the model to additional compartments, for example, that also doesn't increase this in any sort of appreciably scalable way. Okay, so again, I was going to mention real briefly the ABSEER package. If you happen to be fitting spatial SEER models and absolutely nothing else, this may be useful to you. It's very fast. It does nothing but do that. It has some additional features as well. And it's not on-prem, mostly because I'm lazy, but it is relatively easy to install. Additional notes on ABSEER. I don't want to spend too much time on it, but the idea is to specify the model as a group of components. So instead of having to collect together all of the various things that are needed to make one of these things run, you can approach it sort of conditionally, like we do when specifying the thing using sort of arguments from hierarchical Bayesian models. So you specify a data model, an exposure model, a reinfection model, a distance model, where you hand each of these components the various things that are needed. So you would hand an exposure model, a matrix corresponding to covariates upon which you wish to condition, and you give it information about what the prior precision should be on the associated parameters. You tell the transition priors distribution how you want to treat those E to I transitions, etc. So that structure is kind of nice. It allows you to do some sanity checking as a programmer when you're specifying each of these things, as well as when you combine them you pass all of these to the function that actually runs the model. It can make sure that all the dimensions line up for you. So this is a fairly nice way to specify things. The drawback, again, as I mentioned, is that this is just for spatial SEIR models, and if you want this structure to be able to fit arbitrarily complicated models, it's very ugly. So if you want to do something more general, Aaron King has a package called POMP, Partially Observed Markov Processes, that I would recommend checking out. It's very nice, but if you're fitting spatial SEIR models, this is very fast. Additional functionality, you can compute approximate base factors between pairs of models using this. You can retrieve the simulated epidemics and get some statistical summaries, as well as calculation of empirically adjusted reproductive numbers. Now, I think I omitted the slide that addressed your concern about just comparing the distance of the vectors, but it's an important point. So in an epidemic model, we have a net. What was that?
I didn't read the slides.
You did read my slides. You read a previous version of the slide, but now the name. So in this epidemic context, right, we have a natural ordering, we have a spatial ordering and a temporal ordering. So when we think about our simulated epidemic and our observed epidemic, it really is natural to think about just the distance between those things. That's a very natural idea, and that's in fact the only thing that ABSEIR is currently configured to do, is take that distance and use that as your epsilon. There are going to be some challenges, and I'll get to those after I introduce a data example. So the first data set that I want to mention, and this is something we did early that was the example data analysis in the paper, was chikungunya. So chikungunya, it's in the same family as dengue, I believe, and it made a big splash in the Caribbean a couple of years ago. Now, it's an important illness and it affected a huge number of people, but as you can tell, the data is relatively sparse. So on the y-axis of this plot, which you can't read, of course, we have the just an index of the spatial location. And on the x-axis, we have epidemiological week, and then we have some sort of a color scale, just a diverging color scale where red indicates very high counts, and this is a logarithmic scale. Black indicates 0, and gray indicates missing. So you can see almost everything is missing here, right? So this is another attractive feature of approximate Bayesian computation. If you want to use the pointwise sort of Euclidean distance argument, you can just ignore all the places that are missing and still simulate them. That's an attractive feature that I used to tout as a selling point of the package. But nevertheless, you can also see why we're stuck in this highly constrained model setting, right? You're not, unless you observe many replicates of a process like this, it's going to be very difficult to estimate every parameter sort of from scratch. We're introducing a lot of structure like those distance matrices and a lot of prior information through the specification that we've given to try to do anything meaningful with this. And even so, you can get good and bad posterior predictive distributions in the same model. So this is the chikungunya data. The Dominican Republic, which had many, many cases. My parents wanted to go on vacation to the Dominican Republic while this was going on, and I told them that that was not something that was going to be happening. The Dominican Republic had a lot of cases of chikungunya, and you can see that the ABC algorithm, because of the fact that it pays attention to those large deviations, those large squared deviations, does a good job of fitting this, despite not having a ton of structural information about that epidemic shape.
So wait, which is data and which is?
The observations are the dots, and then the model is this sort of smooth line thing, because of course it's sparse, we have missing data even in the Dominican Republic. For Colombia, where there were not quite so many, it did not learn the shape of this epidemic. Now you could increase the number of parameters in the exposure process and try to fix that, but really we're hoping that a relatively simple model will capture all that variability, and here it clearly doesn't. This is one of the things I do like about working with approximate Bayesian computation, is that if you fit this kind of model, assuming you had infinite patients, if you fit a model equivalent to this using MCMC, the posterior distribution of these epidemic counts would actually very closely match. Right? You're conditioning on your observed data and running your algorithm to the point where it's converged. It will closely match this. It's only when you then take the additional step of asking for the posterior predictive distribution resulting from your converged MCMC sampler that you can start to see this kind of pattern. So working with ABC, you don't have that luxury. You have to have a model that generates reasonable replicate data sets to start with, or you're never going to improve upon this. So you can, maybe this approximation is good enough for this problem, but you know, it is clearly not capturing all of the variability, and that's an important point. So, a more recent data analysis, and this is one that I'm actually, is ongoing now, I'm trying to finally wrap up the publication associated with it, involved cholera, which has an entirely different problem. So there is some missingness, especially, so again we have an index over here for location. This is cholera on the island of Hispaniola. Down here we have the, I'm going to screw up the name of the states, either Haiti or the Dominican Republic uses departments, and the other uses provinces. But these are the administrative units for Haiti. These are the administrative units for the Dominican Republic. You can see there's some missingness for the Dominican Republic at the beginning of the epidemic, and then there's 2 weeks for which there was no Pan-American Health Association data for some reason. That's not a problem. We know that our approximate Bayesian computation algorithm will happily charge ahead and just ignore those when computing the distances. But we do have quite a lot of zeros. There is a lot of zero here, and additionally we have a lot of spatial locations. So we're hoping that our model is relatively nuanced. But there are a lot of zeros, and that is, as we'll see, where that Euclidean distance really starts to suffer. So to analyze these data, I first appealed to sort of the terrain. So this is, especially in Haiti, the population relies very closely on just surface water for drinking water and washing and so on, and cooking and so on and so forth. And so understanding how water behaves on the surface of the island, Hispaniola, here is Haiti, here's the Dominican Republic, seemed like it might be an important explanatory factor. And there is actually literature in the non-spatial case that looks at precipitation, for example, and finds an association with cholera outbreaks. So we started with a digital elevation map. So this is just a raster with a measurement of height in meters. And then I performed the highly realistic, highly sensitive, very scientifically motivated experiment where we dropped a cubic meter of water on the entire island of Hispaniola. Sorry. So obviously not a realistic depiction of how water flows, but if you're just trying to pick up things like obvious river networks, it seemed to work relatively well. This is a simple, almost sort of cellular automaton simulation where you keep track at each grid location, each cell in the raster, of how many meters of water are currently sitting on the surface of Hispaniola. Water attempts to go downhill, and if it reaches a flat spot, moves around as if through gravity motion. Now there's a lot going on there. If you break it up into smaller components, you can see some of the complex dynamics that actually emerge, which is what made me hopeful that this would actually be a meaningful basis for fitting these models. So we dropped a cubic meter just on one province, the Centra department. And watch what happens up here. So water goes up into that province and then actually comes back. Meanwhile, it fans out through a valley down here. And you can see, although the color doesn't make it obvious, there is actually a large low-lying area in that region as well. So this kind of a simulation seems promising for getting a rough idea of at least who's downstream of who, which is what we really want to know for cholera. Now, to make it a little bit more interesting, because at least as far as I'm aware, a cubic meter of water has not actually been dropped on Hispaniola at any point in human history, we do have measurements of actual precipitation. And that's something that varies a lot over time. So this is aggregated by week. So obviously at a finer time scale, you would see a little bit more coherence. But we do see that there is spatial heterogeneity as well as temporal heterogeneity in the amount of precipitation. So the simulation that inspired, I don't have a good visualization, it doesn't look as good as when you drop water on the entire island, was to simulate a number of those water particles that was dependent on the amount of precipitation observed in a particular week, and then to run the same simulation to see where the water went, and then keep track of what provinces it went through and ended up in as part of that simulation. And the simulation was actually conducted at a number of different intensity levels because, of course, quantifying a reasonable amount of hypothetical meter cubes of water to drop is a difficult thing to do. So that was a model selection problem that I'm going to wave my hands at for now. But nevertheless, that gave rise, that and all of the other unobserved factors gave rise to the observed cholera epidemic. So this is just the first, or this is the entire outbreak. Again, logarithmic scale. You can see where the pathogen was initially introduced by UN peacekeepers after the earthquake. And then you can see a lot of interesting features. It spreads very quickly throughout Haiti. There's obviously very different behavior between Haiti and the Dominican Republic. You also start to see there does appear to be some spatial structure within each location, and potentially even a water structure. Right? You can see cholera pop up here, then it might pop up there. What connects those departments? Well, they share coastlines. So you might start thinking about both surface water as well as whether or not different areas share coastlines. And then we might think that even just elevation might matter. On an island like this, the way that people interact with the environment is probably different depending on what elevation you have. It's a very hilly location that there's heterogeneity just due to that elevation. And that's what motivated the model that we actually fit. Okay, so I'm going to wave my hands at this because I want to make sure that there's time for questions. This is just a catalog of the various different models that we considered. The fitted model had some of the same features. There's clearly, at least visually similar, spatial patterns. We're getting some activity over in the Dominican Republic, but it's obviously not doing quite as good in the Dominican Republic. And this is just the first 52 weeks, the really exponential growth epidemic phase. So it looks like it might be okay, but it's kind of difficult to visualize two animated choroplasts and see if that's actually a reasonable summary. So if you take a look at the fitted values, things are a little bit more disheartening. So this is just one sample epidemic. I should have drawn a distribution, but I ran out of time. So the points are the observed values. This is summed over all of the departments in Haiti. And the model does an okay job matching the shape. It's missing the magnitude. So there's a problem there. We might look at latent periods, for example. So not terribly bad, but not as good as we would hope. What are we missing? If you look at the Dominican Republic, we do a much poorer job. It's very difficult for the model to describe any process by which the epidemic is actually going to make it to the Dominican Republic in time to have an exponential growth period, and then also die off and then come back later due to rainfall events or transmission along coastlines. So despite having done quite a lot of work to try to include absolutely everything we knew about the transmission pathways, it's still very difficult to simulate epidemics that actually match this in a Euclidean sense. And this isn't just an issue of CPU cycles. The amount of time it takes to do the next algorithmic epoch really does increase exponentially. So when this terminated, it had run, I think, 20 million epidemic simulations and accepted 2. I don't have the patience for that. So work is ongoing to try to improve that. And that's an issue of both model specification as well as algorithmic improvements. Okay. So ongoing work. This is where I'm finally getting to your question that I promised I would get to several times now. So ABC requires us to select that measure of distance between the simulated data sets and observed data. And in practice, a lot of people use summary statistics. Choosing those is problematic. Off the top of my head, to model a complex epidemic that has multiple peaks, multiple different periods of transmission, potentially changing temporal structure, it's not obvious to me what that metric should be. We've tried a number of different choices, none of which really improved on that Euclidean metric. But I think it's important to maybe think about your metrics in terms of how a likelihood would treat them. We're not working with likelihoods here, but there's sort of a likelihood argument to be made. So this is a very simple problem. It's a fair coin toss. The data is 1,000 observations of a fair coin toss, and there were 10,000 simulations. And in each of those 10,000 simulations, what I did is say, okay, I'm going to plug in a value for probability and simulate a whole ton, I think another 10,000 sets of 10,000 coin tosses, and then compute the Euclidean distance between those things. So here, I simulated 10,000 coin tosses of success probability 0.1, took the Euclidean distance with my observed data, and I ended up here. And you see, this looks nice. You know, it has a very clear minimum, if noisy, right around where I'd expect it, at about 0.5. So this is in some sense the information I can get from that Euclidean distance metric via simulation. So that looks good. This is what we expect to see. What happens if I change it just a little bit? If I change it to 0.4, I get that.
What did you change to 0.4?
I change the true probability of success in the data to 0.4, and all of a sudden I get this. So what's going on? Our Euclidean distance metric is losing all of the information about neighboring observations. If you have a likelihood, you're fitting a probability, right? And that probability implies equally over this whole range. If I fit a probability down here, it's going to tell me that that's very improbable. If I'm simulating data, each point is compared to exactly one other point, and all of that information is lost. And it gets even worse. I mean, 0.4 is not far away from that fair point. It gets even worse if you make it 0.3, and I think I had one at 0.1 that looked entirely monotone. And this is something we only noticed because these techniques were performing very poorly in a toy setting. Right? We were doing a toy problem just to teach a student how to implement this algorithm, and it didn't converge at all. And that led to the realization that, oh yeah, this is a terrible distance metric for this problem because it's not a sufficient description of how the two data sets are actually different. So clearly a lot more work needs to be done in that area, providing general purpose distance measure, which don't require either endless trial and error, endless trial and error. The software is still lacking as well. I think everybody, maybe it's just me, everyone may look back at their old projects and think it could have been done much better. ABC here is no exception. It should be more general, it should be faster, and we need to come up with a solution to this distance problem. I don't want to go too much into that since that's something that my graduate student is currently working on and hoping to publish. But there is a lot of work ahead, and I think that there are a lot of applications of these techniques, even if there are important limitations.
So you don't want to compare the likelihoods, for example. Or I guess you could. It somehow has to be related to the likelihood, right?
Yes, exactly. And that's one avenue to pursue in terms of a distance metric. But then you're bringing back some of the associated costs.
Right.
So that's all I've got. Are there any questions?
So I might have missed this, but in your cholera model, are you explicitly modeling the water pathway?
Yes.
And so,
Well, explicitly modeling, no. I'm conditioning on a simulation. And then it receives a parameter, right? So I'm estimating a parameter that allows greater or lesser contact to occur spatially according to a simulation that's done. So I'm conditioning on that simulation in a sort of relative sense. Does that make sense? So the simulation is used to derive one of those D matrices, which is then normalized, and then there's an autocorrelation term that's estimated. So kind of.
yeah, well, so I guess the thing that I'm thinking about for it is, so if you have the rainfall data, and like people have then used rainfall data to force what's happening with the cholera epidemic, do you have that extra spatial layer then, that the rainfall data is like falling over a certain area, but then it's cooling more in certain spatial areas, and that's captured by the way that you're...
Yeah, so I glossed over this just in the interest of time since I didn't want to talk period. We do also have just covariates for rainfall since that's already been found in the literature, and there's a lot of that transition going on within each location, obviously. right? So we do have, and this show, when you fit the models and look at the summaries, I didn't show any actual parameter summaries here, but these are all strongly excluding 0 for those coefficients. So there's a lot of information in rainfall within each spatial location. The same is actually true for the spatial component. We estimate row coefficients which are strongly removed from 0, whereas some of the other distance matrices that we included did not. So I'm forgetting, I think the adjacency matrices actually did not show up as important after having included these rainfall components. So good question. Other thoughts?
Other questions?
So for someone who just wanted to jump into this, and let's say you had a model, wanted to estimate some distributions around some parameters, when would somebody benefit from using ABC versus like Monte Carlo Metropolis AC?
I do firmly believe that if you can, with a Metropolis Hastings model, get an answer in a reasonable amount of time, that's a good way to go. You have a lot of strong theoretical guarantees about the performance. You have well-established methods of evaluating convergence. So I really wouldn't in that case. The answer is when you're having trouble making it converge. In this case, we're benefiting from this sort of dramatic parameter reduction. So the dimension of our parameter space is being reduced by only considering the sort of epidemic basis parameters. If you have a similar feature, that might be useful. But no, if I was working on even a moderate dimensional problem today, I would first reach for MCMC or preferably a more optimized MCMC algorithm like Hamiltonian Monte Carlo, for example. But if you have a situation like this where evaluating the likelihood is expensive, or you have this opportunity for dramatic dimension reduction, it's worth looking at. The other thing I would say is that sometimes it's easier for certain processes to think about how you would simulate it versus how you would write down a likelihood. I mean, often thinking about how the simulation would go is a good way to get to a likelihood also. So it can be part of your problem exploration, because with modern tools like Python and R, it's trivial to simulate data according to models like these. So if that seems attractive, it's not a bad exercise in a complicated modeling setting either. And you can always start simple too. I mean, you can start with that simple rejection algorithm and just see how it goes. For non-spatial analyses in the epidemic setting, it actually works quite well. Other thoughts?
I'll ask a question. So, the Euclidean metric is not going to work well.
Depends.
Well, in your example, it's not.
In ours either.
Yeah, it's not ours either. That's right. That's what I was going to ask. But this is, so that's the least amount of mention before you had to take off. Something involving the likelihood should influence your choice for a metric.
Ideally.
Any ideas? I mean, you've seen what we kind of did, and that seems to work okay for our particular problem. So in an epidemic framework, we've used things like the peak week, so when we get the largest epidemic and the magnitude of the peak.
But as he said, his is 2 peaks.
Is he-
Right.
Yeah.
So as of now, the best sort of published standard is to try to choose meaningful summary statistics for your problem. Just an unsatisfying answer.
It is.
The answer is that I don't have a firm recommendation. I'm looking at a number of options. The paper hasn't been submitted yet, and it's being pushed forward by one of my graduate students, so I can't acknowledge it yet.
Got it.
There are a number of good options. I think that intuition from the likelihood is one good way. Otherwise, more generally trying to estimate a more meaningful comparison based on a distribution, I think is a good general direction.
Okay. Okay. If no other questions, let's thank Grant again.